Hi, everyone. Okay, in this video, I want to define some of the terms we're going to be using this semester, the really foundational terms that are going to help us with language to use when studying motion. So here I've got terms we're going to look at in this video: position, displacement, velocity, distance, and speed. We're also going to talk about scalar versus vector quantities in the context of these definitions. So let's do it. So first, we're going to talk about position. What we mean by position is just where something is relative to a coordinate system. So where something is relative to a given point, or a specific point, I should say, in a particular coordinate system. So what does that mean? Let me give an example here. So imagine that there's a tree. Here's the tree. The leaves on the tree are green because in this example, it's not winter. So if I have ground under the tree, and then I have someone over here, this is Jimmy. So I can say that if this distance here is 10 meters, I can say Jimmy is 10 meters to the right of the tree. So here in this statement, it seems kind of simple, but there's a couple of things that are important to mention. So I've talked about how far Jimmy is from the tree, 10 meters, but I've also kind of established a coordinate system. So I'm using right and left here. So right being this way, left would be this way. So I've said not just how far Jimmy is from the tree, but also the direction that he is away from the tree, which is really important here because position is a vector quantity, which I'll write down. So position is a vector quantity. Because it contains both a distance or a magnitude and a direction. So there's really two pieces of information when we talk about a position. Magnitude and direction. So in the example I just gave, the magnitude was 10. So here's the magnitude 10, and the direction is to the right. I've also kind of got an origin to my coordinate system, which is the tree. So I'm talking about where Jimmy is relative to the tree. I can also, just as an example, let me say there's another person here. So she's over here. This is Susie. So here's Susie. And let's say that Susie is 2 meters from the tree, but she is 2 meters to the left of the tree. So left of the tree. So two examples here. So one where Jimmy's 10 meters right, Susie's 2 meters left. I can kind of abstract this a little bit and think about it just in terms of a number line. So let's say I've got a number line here. And maybe here's where my tree is. I'm going to call this position 0. And then everything's going to be measured from there. So if I count out, let's say 1, 2, 3, 4, 5, I'm just going to mark 5, 6, 7, 8, 9, 10. So here's where Jimmy is. That's Jimmy out here at 10. And over here, I guess I didn't really draw Susie to scale. Here's where Susie is. So Susie's over here. But notice that Susie on this number line is at -2. So the minus here indicates the direction rather than right or left. We've got positive numbers to indicate to the right and negative numbers to indicate to the left. And I can write this as the position of Jimmy, which I'll call x sub j. So the x position of Jimmy is 10. And the x position of Susie is -2. Typically, I could be talking about meters here. I'll just give these units. Meters, meters, meters. So we'll say the position of Jimmy is +10 meters. The position of Susie is -2 meters in the coordinate system that we've chosen. Okay, and to be totally explicit, the right here is the positive direction. The left is the negative direction. We could choose it the other way, but then you kind of flip your number line and have positive numbers going left, negative numbers going right. And we'll see situations where that's the case. Okay, next definition we're going to talk about is displacement. A displacement is a difference between two positions in the context of motion. So what we mean by that is a difference in initial and final positions for something in motion. So what do we mean initial and final? We mean if we start somewhere, that's our initial position. If we travel somewhere else, that might be our final position. And then the displacement would be the difference between those starting and ending points. So for example, if I have a coordinate system, which I represent as a number line again. So let's say I've got my 0 position here. And if I count back, let's say 1, 2, 3, 4, 5 spots here. Let's say I started here. So this is my initial position. I'm going to call this x sub I for initial. This would be -5 meters. That's my initial position in this coordinate system where right is positive and left is negative. And let's say I moved from that initial position. So I walk to the right and I end up out here. So how far is that? 1, 2, 3, 4, 5, 6, 7, 8. So my final position out here is 8 meters from the origin. My displacement is the difference between the initial and final positions. So my displacement, delta x, delta meaning change, so change in x, is the final position minus the initial position. So in this case, the displacement, delta x, is 8 meters minus -5 meters. That works out to 13 meters. So this kind of makes sense. You can think of that as there's 13 meters of difference between those two positions. The -5 there kind of counts all of that distance. You have to be careful with signs here, as I was. You've got to make sure that you're always taking the final minus the initial, and you're keeping track of which positions are positive and which are negative. So let's look at another example here. Let me call this green example 1. Now let's do another example. So let's say another number line here, different example. So I'll put my 0 right there. So now let's say I've got, I'm out here now. So let's say I'm out here. Some initial position. So this is 10. So my initial position is 10 meters. But then I walk back to the left. So I go back to the left. Oops, I forgot my legs. Go back to the left to here, let's say. So I walked left to here, to some final position, which is now 4 meters. So I'm closer to the origin than when I started. So now, if I look at my displacement still the final position minus the initial position. It is always the final position minus the initial position. Okay, so delta x will be here. My final position is 4. My initial position was 10, so it's 4 minus 10, which is -6 meters. So notice here This distance from initial to final was 6 meters, but this minus sign indicates the direction of the motion. So minus meaning kind of moving to the left. The positive 13 in the above example meant there was a distance of 13 between the initial and final positions. And the fact that that was a positive 13 meant that we were moving to the right, moving in the positive direction here. So displacement here is also a vector quantity. And I'll write that down. So displacement is also a vector quantity, which is really important to keep in mind. And the sign of the displacement indicates direction of motion. Okay, so let's take a look at velocity. So, all right, velocity. What is velocity? So velocity is also going to be a vector, which we'll talk about in a sec. And velocity is a vector that tells you the speed in a particular direction. So when we look at velocity, we get two pieces of information. We get how fast and in what direction. So I guess maybe because I'm going to define speed later, let me call this how fast. How fast in a particular direction. So if you consider what exactly that means, we're talking about displacements and times. So fast is a measure of how quickly something happens. So a certain displacement could happen faster if you moved in that displacement over a shorter period of time. So let me define something that will help us quantify that with an equation, which is called the average velocity. So the average velocity for some time, which I'll call V for velocity sub AVG, just to be average, but I don't have to write the whole word. That's equal to displacement over a time interval. So if we look at how far we went and how long it took us to move that displacement, we divide those two things, that gets us the average velocity for the time interval. So if we write this like a final position minus an initial position, that's displacement, divided by a final time minus an initial time. So what we mean by final time and initial time are the moments in time when you are at the initial position and the final position. So let's look at our green example again. Forgot to label purple example. So green example, example 1. Let's say that when I started, I was over here at the initial position. Let's say I started a stopwatch. So, and when I did that, it started ticking up from 0 seconds. So we're measuring time in seconds. And when I walk all the way over to the final position, I look down at the stopwatch and I notice that the stopwatch says that it was 5 seconds. So my initial time was 0 seconds, just whatever time the stopwatch said. And my final time was 5 seconds, whatever time the stopwatch said. You can measure initial and final time however you want. If you want to use just a wall clock, you have some other timing mechanism, you can do that. But to calculate the average velocity, which is how fast and in what direction, I'm going to use the displacement and that time interval. So in this example, in example 1, the average velocity is the displacement x final minus x initial over the time interval t final minus t initial. So we already figured out what the displacement was up here. X final minus X initial was 13 meters, positive 13. And the final time is 5. The initial time is 0. So the time interval is 5 seconds. And our average velocity is 13/5 meters per second. That's our average velocity for this time interval. Notice that if the time interval was smaller, the average velocity would be bigger. If the time interval was bigger, the average velocity would be smaller. So things that take longer are slower. Things that take shorter are faster. Our unit for velocity is meters per second. That's our standard unit for velocity. So that's a distance over a time, meters per second. Let's look at the case 2, the purple case. So if we do purple case 2, average velocity in this case, same thing, the final minus initial positions for the displacement, and then the time interval, t final minus ti. So we worked out what the displacement was before. It was -6 meters. Well, we need to know the times here. So let's say we started at a time, maybe I let my stopwatch run a little bit here. So I started at 3 seconds. And then my final time was 5 seconds. So now the final time minus the initial time is 5 minus 3. That's 2 seconds. So this is -6/2 meters per second. Or I guess I can just say -3 meters per second. That's the average velocity in this time interval. Notice again that this is still negative. And what the negative means, again, in this case, is that we're moving back towards the origin, we're moving left. So again, in the green case, the positive velocity means that on average, we're moving to the right. And the negative velocity in the purple case means on average, in that case, we were moving to the left. So velocity is a vector 2. I'll write that up here. It's a vector. So the sign of the velocity indicates the direction of motion again. So same thing as for displacement. All right, let's look at a couple other quantities. We're going to look at now distance. Okay, so distance is the length traveled on a specific path. This is a little bit different than displacement. So displacement was just a difference between an initial and a final position, but distance is a little bit different. One way it's different is that it's a scalar quantity. So let's look at another number line here. Okay, so let's say here's my origin. That's 0 in my coordinate system. And let's say I've got initial position right here. So that's my initial position, -4 meters. All right, so let's say that instead of moving in a straight line to the right, I now move to the right for a while and then come back to the left. So let's say I'm going to take a path that starts at -4 meters, goes out to the right, and then turns around and comes back to the left a little bit. So that just looks like me starting here, walking to the right, stopping, turning around, and coming back to this position. So at this position, I'm now at 5 meters. We can calculate the displacement travel on this path. Even though I went further out to the right before coming back, the displacement is still the same. So displacement here, delta x, is still the final position minus the initial position. No matter what path was taken between the final and initial positions, as long as those positions are the same, the displacement will be the same. So I can calculate that just as 5, that's the final position, minus -4, that's the initial position. So my displacement is 9 meters. Okay, distance is a little bit different. So distance is the length traveled on this specific path. So how far did I actually travel on this path? Well, I came from -4 and I went out here all the way out to 9 meters, it looks like. So I traveled 13 meters when I was doing that. So on that first leg, I traveled 13 meters, and then coming back, I traveled another 4 meters before I ended up back at 5. So in total, I traveled 13 plus 4 is 17 meters. So the distance I traveled was 13 meters plus 4 meters is 17 meters, even though my displacement was only 9 meters. This doesn't contain any information about the direction I was going. It just says, what was the total length I traveled on whatever path I took? And there's no reason the distance and displacement have to be the same. In general, they'll be different. They'll only be the same if you move one direction in a straight line the whole way. Okay, so that's distance. One more thing I want to talk about is speed. So speed is how fast you're going, and with no particular direction in mind. So how fast something is moving. So again, this is a rate. Velocity is a rate too, but we can talk about an average speed here, not as displacement over time, but distance over time. So S for speed, average, would be the distance over the corresponding time interval. So if we look at the example above, the distance traveled on the path we took here, the blue path, was 17 meters. If we put some times here too, so let's say I started my stopwatch here and at 0 seconds, and my final time was 10 seconds. Then my average speed for that motion would be 17 meters divided by 10 seconds. So I'd have 1.7 meters per second is the speed. Notice that if we calculated the average velocity here, so if we calculated velocity average, which we calculate as displacement over that time, delta x over delta t, then we'd have 9 meters over 10 seconds, so 0.9 meters per second. So in general, you're going to have different distances and displacements in most cases, and different average velocities and average speeds. While average velocity can be negative, as we saw in a previous example, the average speed can never be negative. So the speed, again, is a scalar. It's only telling you something about how fast. It doesn't tell you anything about direction here. They're always going to be positive. So distances and speeds will always be positive. They're just magnitudes, whereas displacements and velocities can be positive or negative depending on the direction of the motion. So that's it. Hope that was useful. See you soon.